So I left you guys last week with kind of this weird structure, and I named it for you. And I don't think that we had fleshed out enough about this last part of our nomenclature, our naming system. Can someone remind me, in the 4 generic parts of a name, what does the root inform about a molecule? Good. Number of carbons in the parent chain. And while you're on that, Natalie, parent chain is decided as? The longest carbon chain with the highest priority functional group. And this semester, your highest priority functional group will be alcohols. So I showed you guys several layers higher than alcohol, but you will not have to name those compounds. I want to give you that big picture so that you can go out and explore the world. I just don't, your textbook actually names just alkanes, then alkyl halides, then alkenes, or then alcohols, then alkenes, then alkynes. I think it makes more sense to have a big picture idea. We're going to test in parts. First, you'll be tested on alkanes and alkyl halides. Then you'll be tested on alcohols and alkenes and alkynes. So, big picture, test as we build up. Okay? What does the suffix indicate? Good. And technically, there's 2 parts to the suffix, right? All suffixes will have either ane, ene, or ine, which tells us really the higher priority hydrocarbon, and then they get stoppered by something else that describes a different heteroatom or carbonyl functional group. So OL for alcohol, AL for aldehyde, oic acid for carboxylic acid. The locant between the root and the suffix tells us what? Where that highest priority functional group is on the carbon chain. And what if we have multiple of that functional group that shows up in the suffix? What if I have 2 alkenes? How does the suffix change? Yeah, we get that multiplier added in, di-ene. And how does the locant change? I need 2 locants. I need as many locants for as many of that functional group as there are. I guess I didn't give a great example with this last week, but we looked at methane tetrol, which didn't have any locants, because what other carbon can they be on besides the 1 carbon of methane, right? But if you have multiple alcohols, you need to name multiple locations where those alcohols show up. Okay, then we got to the prefix. The prefix describes everything else. If there's an atom, a carbon, a heteroatom that is not named in the parent chain, not named in the suffix, then it has to be named in here. And even compounds that can be named in the suffix can get kicked out of being in the suffix by higher priority groups, and then they show up in the prefix. So, one thing that we always put in the prefix are the halogen groups, the halos, because we're going to call these chloro, bromo, iodo, and we don't use this one very often. I kind of skipped right over it, fluoro. And what happens if we have multiple of these? Then they get multipliers. You get dichloro, trifluoro, tetraiodo. The multipliers just go on. If you have carbon groups, this is where I want to dig in a little bit more. You assign a root to that carbon substituent, that chain coming off. How would you decide what root goes with that carbon chain? Well, if it's a 1 carbon chain, give it meth. 2 carbon chain, give it eth. 3 carbon chain, prop. 4 carbons? Bute, 5 carbons. Pent. It's the same roots that show up in the prefixes to describe how long a carbon substituent is. So how do we distinguish these carbon groups in the prefix from the carbon groups that are already named in the actual parent chain? We change the suffix. Instead of having methane, we get this suffix methyl. And that carries down for all of them. A 2-carbon chain, ethyl. A 3-carbon chain, propyl. You guys are all familiar with isopropyl alcohol. That's what this is. That's the suffix you get at the end, just that YL group. That makes sense?
Sorry, I was late. And that's for all of the carbon chains?
All of them, yep. But we're going to talk about some odd carbon chains. We're going to look at these carbon chains that aren't just straight lines. And we want to be familiar with how to name them. So, what I'm going to do is draw one long parent chain, and we're going to look at some odd carbon chains that come off. And by odd, I mean common, but not just straight chain. I'm just doing this as a way of showing all of them at once, making a list. You okay with that? Feel free to organize this how you need to in your notes. We already looked at a 1-carbon chain, CH3, and 2-carbon chains, CH2CH3, methyl and ethyl. But when it comes to a 3-carbon chain, there are 2 ways that I can organize it. This linear direction is propyl, which is sometimes called N-propyl. What do you think N stands for? Not north. It's pointing south right now. Normal. Straight chain. If, however, you take one of these carbon groups and connect it off of the first carbon, you get this little Y shape. This is an iso group. This becomes isopropyl. So when you're thinking about isopropyl alcohol, that OH is coming off of that center carbon. This is a common name. Notice how it has no systematic structure to it. If you don't know what that iso group looks like, that little Y, you don't know what it is. How could we name it systematically? First of all, we have to use parentheses because this is a substituted substituent. It's a group coming off of the parent that has a group coming off of it. So in parentheses, we would call this 1-methyl ethyl. Aiden, how many carbons does propyl inform us about?
4.
Propyl?
Oh, 3.
Right.
Yeah.
How many carbons does methyl plus ethyl inform us about?
4.
No.
3.
1
Counting the...
plus 2.
Oh, okay.
So this is a systematic way of renaming isopropyl, 1-methyl ethyl. If you were to rename N-propyl, it would be 2-methyl ethyl, but that doesn't make any sense because that's just a straight chain of propyl. Do you see where this name comes from and why it can substitute isopropyl?
So should we name things ethyl or propyl when it comes to...
It's your choice, but I will say you do need to know isopropyl. We'll be talking about isopropyl groups a lot. But on that PLO bonus point required assignment that you have to submit, The last page asks you to name substituted substituents, both with their common names and their systematic name, so that you get used to applying both of them. I want you to be familiar for sure with this, but I want this to also make sense to you. Now, we're going to come back to some of these. I'm going to point out some details in a little bit, but some more that I want you to know. 4-carbon chain, straight. What can we name it? Not just butyl. We can name this N-butyl. Although if you call it butyl, everyone will understand. What if I take the last carbon and I move it down a position? Do you notice how I get that little Y thing sticking off of the end of my substituent? The only difference is that now it's not directly off of the parent chain, it's 1 carbon off of the parent chain. This is isobutyl. Take a minute to try naming this systematically. What is the parent chain of the substituent, and how long is the substituent coming off of that substituent? What is the prefix you give to your prefix? Then, what number is that substituent coming off of? Is it the first carbon from the parent chain, the second carbon from the parent chain, the third carbon? By the way, this is how I kind of encourage you to name it, is work backwards. Find that longest part, then find the name coming off of it, then find the number to describe it. Elliot, how long is this carbon chain? What root would you give it? Yeah, so we can call this propyl. This is a 3-carbon chain coming off the parent. Yvonne, how long is my 1-carbon substituent coming off? Whoops, sorry, I gave that away. How long is my substituent coming off of this 3-carbon chain? 1 carbon. So we give it the root methyl. This is a methyl propyl. And what position, Kiara, off of the parent chain do I find my methyl? The first carbon, the second, or the third? Right. So this is 2-methyl propyl. All right, now I want you to draw 1-methyl propyl. Draw the 1-methyl propyl substituent. Look on with the people nearby. Did you agree about how long the carbon chain was, where the substituent came off? thought it was coming off of the parent chain carbon too.
No, you're good.
No, these are, so one methyl, oh yeah, okay, so these are prefixes. Yeah, we put them on. Our parent chain is what, like 15 carbons? Yeah. So this would be 2-methyl, 4-ethyl, 5-N-propyl. Yeah. And then like a 15 You got it. Pentadecane. Pentadecane. Anybody feel brave enough to draw their 1-methyl propyl substituent? No? By the way, part of nomenclature is being able to name from a structure and draw from a name. So this skill is something I want you to have back and forth. Perfect, great job. 3-carbon chain coming from the parent. 1, 2, 3, not counting the parent. Off of that first carbon, a methyl group. 1-methyl propyl. What do you suspect the common name for this is? I don't think you'll get it. That's okay. Oh, you did get it. Good job. This is sec-butyl. There's a dash there. This is also sometimes just called S-butyl. Sec is describing something about the nature of this carbon, assuming that it's not bonded to another carbon. This is me cutting that bond. I'm going to describe this a little bit more in a minute. But for right now, I just want you to notice, we're saying sec is short for secondary. And this carbon here is a secondary carbon. We'll describe what that is in a minute. There's one last way that I can arrange butyl. That's if I take this last carbon here and I move it also to be coming off of my carbon chain. This is called tert-butyl, short for tertiary. And once again, can be abbreviated with just a T. But its systematic name? How long is the longest carbon chain in the substituent? Just 2 carbons. This is an ethyl group. How many carbons coming off of that 2-carbon chain? Here's my longest chain, 1, 2. And here are 2 other carbon groups coming off. Both of them are methyl. So I need a multiplier. That multiplier is di. This is a dimethyl. And because I have 2 substituents, I need 2 locants. So the systematic name here is 1,1-dimethyl ethyl. Now someone will argue, why can't I just name it 1-ethyl dimethyl? Or sorry, 1-dimethyl ethyl. And just assume that both methyls are off of carbon 1. Because we're trying to be as redundant as possible. So we're going to say that both of them are on position 1. Each locant, each substituent gets a locant. Okay? Some other, these are a little more odd, but I do want you to be familiar with them. I told you guys that you could abbreviate a benzene ring as pH. That's because we call this a phenyl substituent. I know it might surprise you that benzene does not have to be the longest carbon chain. You'll learn a lot more about benzene nomenclature in OChem 2, or you can watch my YouTube channel. I just talked about it last week with OChem 2. But you won't have to name benzene at all. On that PLO assignment, you will, but you'll name benzene as a substituent of an alkane chain. If you have, oh, and I'm sorry, I realized I went with the wrong color there. If you have a 2-carbon alkene, this group is referred to as vinyl. And I introduce that now because we will introduce a new functional group later in the semester called vinylic halides. Halogens that are connected to alkene groups. When we look at spectroscopy, we're going to describe vinylic hydrogens, hydrogens that are attached to alkene groups. If I add a CH2 group in between, this is called allyl. And at the end of the semester, we're going to be doing some reactions with allylic halogens, allylic alcohols, those that are attached at a CH2 position adjacent to an alkene. I'm trying to think if I have other groups, but I think that for this semester, that's really all you're going to see. Maybe just one last one that is so easy and useful. I'm going to put this as OR, which makes that what functional group? An ether. It's an oxygen with carbon on ether side. If I want to name an ether as a substituent, I need to know what this is. I don't have it right now because it's R. So I can abbreviate R as ALK. Remember, alkane, alkene, alkyne. This becomes alkoxy. ALK for R, oxy to indicate the presence of the oxygen. If I have methoxyethane, then I have a OCH3 attached to a 2-carbon chain. Very easy substituent to name. These are the predominant ones that you'll be seeing in our class this semester, so I want you to be familiar with them. There is another thing to say about nomenclature, or sorry, with these prefixes. These prefixes are going to be alphabetized, and I want to show you some odd things about the alphabetization techniques. I'm underlining it in orange to draw your attention to the oddballs. Methyl, ethyl, propyl, butyl, pentyl, etc. Always alphabetized by that first letter. Isopropyl, alphabetized by I. Isobutyl, alphabetized by I. N-propyl, P, not N. N-butyl, B. Sec-butyl, B. Not sec, not S. Tert-butyl, B. Not T. Tert and sec and N are all descriptors of butyl and propyl. Iso is a common name. It's a new name. It's not a description. It's a name you have to recognize. So common names get alphabetized by what they are. Descriptive names don't get put in the alphabetization sequence. Systematic names, inside the parentheses, you multiply by whatever letter comes first. M, 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 D. If you have a substituted substituent, you just alphabetize it by the first letter. This is an odd case. Multipliers are only included in the alphabetical order. Never by multiplier. Except if first in a parentheses name. Does that make sense? The multiplier is not the group. We're going to alphabetize the groups. And if I have multiple of that group, I just say that I have multiple of that group. But I alphabetize by the group. Unless that group is in a parentheses, in which case that's its whole name. Then you do multiply by that. Never alphabetize by multipliers except if that multiplier comes first inside of a parentheses. Deal? The last thing to say about prefixes. Number the chains to get the lowest locant set. At first point of difference. Hopefully you guys remember that. That's the same rule that we used for our locants and the suffixes. So even still, you're going to prioritize the lowest locant set for the highest priority functional group. Then if all else doesn't matter, you look for the lowest locant set total at the first point of difference. What happens if you number from the left and you get a locant set 1, 1, 2, let's say 1, 1, 2, 2, and you number from the right and you get 1, 1, 2, 2. What happens if you get a tied locant set in either direction? You have to know which way to go. If there are two lowest locant sets, we need to have a rule. Tie goes what would you say? If it doesn't matter which direction, to get the lowest locant set at the first point of difference, tie goes to how about first alphabetical? That way you can get a lower locant set at the front of the name. And that's the rule. Tie goes to the first alphabetically. So now we apply it. When naming a compound, I recommend that you first find the root. Second, find the suffix. Third, find all substituents. And what I really mean by that is also get their locant set. And then lastly, alphabetize them. I'll walk you through this first one. The longest carbon chain I can find is 5 carbons long. It doesn't matter if I go up into one of these labeled CH3 groups or if I just go straight across. 5 carbons, pentane, or really just pent. Suffix, only alkane functionality. Alkyl halides don't change the suffix at all. So this is pentane. Find all the substituents. I've got 2 bromines. That's going to come in to be dibromo. I've got 2 methyl groups. That's going to come in to be dimethyl. How do I alphabetize dibromo? What letter? B. And how do I alphabetize dimethyl? M. But I also need locants. What locants do I get for the 2 bromines? 2 and 2. I have 2 bromines, they both need a number, right? So 2 and 2, oops, sorry. I kind of jumped over this. They could be 2 and 2 if I come from the left. They could be 4 and 4 if I come from the right. And the methyls, 2 and 2 if I come from the right, 4 and 4 if I come from the left. I'm going to write this as my 2 possible locant sets, 2, 2, 4, 4, or 2, 2, 4, 4. This is if I number from right to left. This is if I number from, I said that wrong. This is if I number from left to right or right to left. You agree?
Doesn't the tie go to bromine? Oh.
And that's what I jumped over.
Oh, okay.
I wanted us to verify first that it doesn't matter which way it goes, there's a tie.
Sorry, I thought you were saying you could write it as either way, and so I was tripped up a little bit.
Well, dibromo is always going to go first. But in this case, I have to give bromine locant 2 because it's tied, so the first goes alphabetically. Gotcha. So 2,2 dibromo. Uh, 4,4 dimethyl. Pentane. Do you agree? I do want to point out one small thing. It's a feature that I haven't talked about yet. There are commas and there are dashes. They play specific roles. Commas only separate locants from each other. Dashes separate words from locants. And the words are never separated. Notice how it's methylpentane. It feeds right in. This is one long word. Here's what I want you guys to do. Before we move on to this next one, I want you to draw this structure based on how I name it. Figure out what's wrong with that name and rename it correctly. This is a structural isomer. 2,3 dibromo, 4,4 dimethyl pentane. Draw it by its name. I recommend first drawing the root. Pick a direction you want to number, and then add those substituents there. Once you've drawn it, forget about the name I gave. It's wrong. Rename it. Figure out what went wrong in that first name. And feel free to collaborate during this. You're not being quizzed yet. You're kidding. You're doing it right. A little weird with the methyls. Why don't you write out the locus set, you number it from left to right, and then just underneath it, write out the locus set, right to left. Compare the two possible locus sets. You drawn it right? Good job. You too, Jackie. You guys got it. So now, sum the name. There's still two bromines. So we will still call it dibromo.
But is the number the issue, like next to it? Like I'm starting to think like because there's.
Well, what I will say is it's not 2-bromo, 3-bromo.
Yeah, no, I know it's not that. Yeah,
Why don't you see if there's something, it's alphabetized correctly, right? Why don't you see if it's something wrong with the locant set? So here's our root. You didn't watch the videos yet? We'll find some time this week. This is our root. 5 alkane. This is the root of the suffix. So we're going to have a 5-member chain alkane, just like this. 1, 2, 3, 4, 5. This is called the prefix. It's describing everything else that isn't alongside the chain. 2 bromines, 2 1-carbon chains. You're actually all caught up. We just talked about that too. And here is where along the carbon chain those groups show up. So to draw it backwards, start by drawing the root, 5-carbon chain, and then draw 2 bromines, 1 on the second, 1 on the third carbon, 2 methyls, both on the fourth. Sarah, you've got it. You've got it. So have you looked at the name going from the left to the right? The locant set going from the left to the right? Mm-hmm. Yeah, you've drawn it right. So you've got a locant at 2, a locant at 3, 4, and 4, which is why we have the name we did. What if you numbered it from the right? Go lowest number to highest. 1, 2, 2, 2, 3, 4. You just put the words in there alphabetically. Their locant
yeah.
is totally separate. Yes, good job. That's it.
That makes a lot of sense. Okay.
Nope. Oh, for a group, yes. But the
It's
groups
possible to remove one of
should
them.
be going in alphabetical and get whatever numbers they have. Yep.
Well, it's possible to remove 2 whole
Great
groups.
job. Oh,
Like, you're able to reduce the number.
Bromos
The
still comes
value of
before.
each 2 numbers in there by 1. Yeah,
That's okay. No.
I've always prioritized.
So this locant set is 2, 3, 4, 4. I've got a substituent at 2, 3, 4, 4. This one is 2, 2, 3, 4. So write those out like I did in orange and compare them. The error in this name is what? The locant set is not correct here. So I'm going to try to visualize it a little bit better than I just did on this top example. If I number it from left to right, I get 1, 2, 3, 4, 5. This is how I get 2, 3, 4, and 4. A bromine at 2, a bromine at 3, a methyl at 4, a second methyl at 4. That's my locant set. I like to write it out so that I can more easily figure out the first point of difference. What if I number it from right to left? 1, 2, 3, 4, 5. Now I get a methyl at 2, a methyl at 2, a bromine at 3, and a bromine at 4. Where is the first point of difference? What numbers am I comparing? 2 and 3. This is my first point of difference here. Both of the structures have a substituent at 2, but one of them can have 2 substituents at 2. The other naming only has 1. So did I choose red or green? Because I'm going for the lowest locant set. Now I'm going to be honest, I chose this example intentionally because this really scratches an itch in your brain. You get the lower numbers in front and the alphabetical things in front. Here's the most common mistake I see with renaming this. Students will come back and call this 2,2-dimethyl 3,4-dibromo-pentane. What's wrong with this? It's just not alphabetical. That's the only issue. So when you see this first example, you go, right, lowest number to highest number. But that's not how we arrange the things in the name. We arrange the name by the alphabetical order of their substituents, whatever their locants are. You will see locants that climb numerically as it goes alphabetical. You'll see locants that descend numerically as it goes alphabetical. And you will see gibberish, randomness. So this is not correct. And the correct name is 3,4-dibromo 2,2-dimethyl pentane. Can you tell me how much of that name is prefix? Everything but pentane. Most compounds are just prefix. Because you can only describe so much by the longest carbon chain, and then you have to name everything else going on in the prefix. So don't be daunted when a name looks really long and it's all substituents. Can we name the structure up top? First of all, where do I start? On my linear chains, I have to start on the left or I have to start on the right. Now that's a little bit misleading. I can start top and bottom. On linear chains, I have to start at a chain end. Where do I start in a ring? We talked about this a bit last week too. Anywhere, correct? Wherever makes the most sense. If I have an alkene, I need to start at that alkene and number through it. If I have an alcohol, I need to start there, regardless of if there's an alkene. But if I don't have an alkene or an alcohol, these groups, alkyl groups, by the way, that's what I wanted to put here. These are all alkyl, A-L-K-Y-L, kind of like alkyl halide. If I have just alkyl groups and halogen groups, they're tied with each other. They're equal priority. The only reason I would give a halogen a lower number is if it came alphabetically and there was a tied locant set. So where should I start numbering this? What are the possible lowest sets, lowest locant sets that I could look for? I could start at chlorine, and I could go counterclockwise. And I get a locant set, 1, 3, 4. I could start at isopropyl, and I could go clockwise, and I could get a locant set 1, 2, 4. I could start at isopropyl and go counterclockwise, and I could get 1, 4, 6. I could start at tert-butyl and go counterclockwise. And I could get a locant set 1, 2, 5. And there's a few more too. Which locant set should I choose?
One.
Red? Red beats green because 2 is lower than 3. Red beats orange because 4 is lower than 5. So there were 2 reasons why red is correct. But you also can maybe see there's 2 substituents next to each other, and then 1 substituent a little bit further away. So let's just number so that those 2 substituents get named first, numbered first, and then go whichever direction is shortest to get to the other one, right? Let's write out the root first. What's the root and suffix of this compound? Not cyclohexyl, because that's the suffix for our prefix. Cyclohexane. Because all we have is alkane functionality. What are the names of my substituents? What's this little Y group at the top? Isopropyl. How does that get alphabetized? I. What is that chicken foot to the right? Tert-butyl, which I can write as T-butyl. And how does this get alphabetized? B. And then lastly, the Cl. Chloro, which gets alphabetized by C. So what comes first? A, B, C, D. If you thought you'd be done singing your alphabet, you're wrong. You should be singing it during the exam. Tert-butyl. Oh no, that's not enough. I need to describe where on the carbon chain tert-butyl is. 2 tert-butyl. Then what? 4 chloro. And lastly, 1 isopropyl. Remember I said sometimes numbers will go with alphabetical order, sometimes numbers will go against alphabetical order, sometimes numbers are just gibberish. The locant does not decide how the substituents are organized. What do you think? Pretty good? Pretty weird? Any questions on it? This is pretty standard. This little exercise I gave you will be on your unit test, will be on your midterm exam, where I give you a compound that is named incorrectly. You need to show me that you can draw it by the name and that you can identify what is wrong. Was the longest parent chain not chosen? Was the wrong locant set put in? Was the name just not alphabetical? One thing I will tell you about those questions, they're never trick questions. The number of times I get students that are like, the name is the same, nothing was wrong. Nope. And the number of times people will give me a structural isomer and they'll say, oh, you meant to put the 2 methyl groups on different carbons. No, I called it 2,2 for a reason. They're on the same carbon. They're never trick questions. It's just meant to identify, can you draw it correctly, even if it's an incorrect name? And can you identify how to correctly name it? What's wrong with it? Here's a fun thing. AI sucks at this problem. And it will die on the hill that it is good at it. Over the summer, I fed it one of my problems, 1-tert-butyl propane, rename it. And it said, oh, well, this is 2,2-dimethylbutane, which isn't far off, but it's not right. So I plugged it in again, give it to me again. Over and over and over until I started pushing it. Just admit that you can't solve this. You know what AI said? Well, it's not my fault that it's named by breaking the rules of IUPAC. I'm sorry, that's the whole point, is to see that you can reinterpret the IUPAC rules. And AI is not very good at it. I did find that ChatGPT has a chemistry AI. It's like extra trained on chemistry. And that one got it wrong the first time, but got it right the second time, after it like literally died while loading twice. But once it finally survived its loading, it gave it to me correctly the second time. So be wary, that's all I'm saying. I would trust a human more than I would trust an AI on helping you solve those types of problems.
I have more of a story, so I'm sorry. I have a friend that works in computer science, and they were making, I forget exactly what it was, but they were taking different AIs and putting it onto their server. And they were asking me for my chemistry questions from my previous term so that I could test it.
Yeah.
And one of them, the deep sleep one, it continued to give an answer for 6 hours until we had to force stop it.
Oh.
It didn't actually answer, it just went for 6 hours saying different things.
It's crazy. And yeah, AI doesn't think, AI calculates as close to what human thinking feels like. So AI has been proven. Apple released a paper recently saying that AI is not thinking, and when you give it logic, it shuts off. Even when you give it the solution, it doesn't look at that solution and just spit it back out. So it's very strange. Be careful, be wary. Use it for other things and not that activity. One thing before I let us have a quick break today. We're going to be talking about this term a lot this semester, and that is regiochemistry. Tell me what that evokes in you. What do you think? Regional chemistry, like the Northeast, the Deep South, the Midwest. Kind of, but on a molecule. It's what region of the molecule chemistry is happening at. Or it's the difference in chemical properties based on the regions around a part of the molecule. So here's some of the terms that we're going to use, especially in this section. We're going to describe degrees of carbon substitution. This is not degrees of unsaturation. And it's not when carbon is substituted with just anything. This is the number of bonds to other carbons. If we think about a carbon that has no bonds to other carbons, we would just call it unsubstituted. That's like a methane group. So we could put methanol here as an unsubstituted carbon. Or we could put methyl iodide as an unsubstituted carbon. That is a methyl halide and a methyl alcohol. If your carbon is bonded to one other carbon, we call this primary, and we represent it with 1 degree. So all I need to change here is to have a second carbon in my structure. But I can have as many carbons as I want in my structure, just so long as the carbon I'm talking about is primary. Both of these carbons are primary. And this carbon, the benzylic carbon, the one coming off of the benzene ring, is primary, attached to just one other carbon. If your carbon is bonded to two other carbons, secondary, 2 degree. This is isopropyl alcohol. The carbons on the edge, on the ends, are primary carbons still, but the central carbon is bonded to two other carbons, secondary. This structure here can be called sec-butyl chloride. Why is it called sec-butyl chloride? This type of nomenclature is functional class. I name the functional group at the end, like isopropyl alcohol, sec-butyl chloride, instead of calling it 2-chlorobutane. I can call it sec-butyl because we agreed that when the parent chain connects to the substituent, at this, the secondary carbon, that we call it sec-butyl. I do want to point out the most horrendous mistake they made in calling this sec-butyl instead of just forcing you to call it 1-methylpropyl. And that is, in this structure, if this molecule were real, what is the actual degree of substitution at that carbon? How many carbons is it bonded to? 3. It's the secondary carbon bonded to methyl and ethyl. It's also bonded to the parent chain. So it's a sec-butyl substituent ignoring the parent chain carbon, right? It's a lot more obvious when you look at it in a structure like this, where it's a sec-butyl group, literally, because the only other group is the halogen. How many other secondary carbons in sec-butyl chloride? Just one other carbon. How many unsubstituted carbons? No, there are 0 unsubstituted, but there are 2 primary carbons. And here's another terrible thing. We call primary carbons methyl groups, which is different than being a methyl carbon, an unsubstituted carbon. It's great. All right, if there are 3, we call it tertiary. So this structure here is tert-butyl alcohol, or tert-butanol. How many tertiary carbons there? Just 1. What are the other 3 carbons? Unsubstituted, primary, secondary. They're all primary. They're all methyl groups, CH3s, primary carbons. Why is it that this carbon is called tertiary despite having all of its hydrogens substituted? That carbon is not bonded to any hydrogens. because we rank substitution by the bonds to other carbons alone. It doesn't matter what other atoms it might be bonded to. It's just how many carbons it's bonded to. Here's another example. I'm going to abbreviate a benzene ring here with pH, and I'm drawing a tertiary carbon coming off of it. Coming back to this confusing part, we call tert butyl groups tert because of that tertiary carbon. If you ignore the bond to the parent chain, like if you imagine tert butyl alcohol. But as it is, that tert butyl group on the parent chain is actually how substituted? Not bonded to 3, bonded to 4. So what do we call that? Quaternary. Those of you in biology may know about quaternary structures. I think that's when 2 proteins come up close to each other, like hemoglobin forms quaternary structures. Here we're just saying a carbon bonded to 4 carbons. Can I have a quaternary functional group, a quaternary alcohol, a quaternary alkyl halide?
No,
There's not enough bonds. If my carbons, 4 bonds are all taken up to other carbons, then I can't have a methyl halide, a primary halide, a secondary halide, a tertiary halide, because there's no bonds left. So here is something affectionately known as neopentyl, but looks like an X, and is systematically called 2,2-dimethylpropane. But if you want to look at a more realistic looking structure, look at 2,2-dimethyl cyclohexane. I'm sorry, 2,2-dimethyl. 1,1-dimethyl, lowest locant set. 1,1-dimethyl cyclohexane. How many primary carbons? 2. The 2 methyl groups. How many secondary carbons? How many carbons bonded to 2 other carbons? 5. Here, and all the way around the ring. Would you agree? Yeah? Point at that carbon and then count how many other carbons are bonded to it. And how many tertiary? 0. This structure has no tertiary carbons. But it has this quaternary carbon right in the center, where the dimethyl groups are. All right, so you may be thinking, is there no way to get an unsubstituted carbon into a larger molecule? And the answer is no, you can if you have something like this. This is methyl propyl ether. You can also call it 1-methoxypropane. This has 2 primary carbons, 1 secondary carbon, but this carbon is attached to 0 other carbons. So that's a methyl carbon. That's an unsubstituted carbon. That's our regiochemistry. Looking at carbons and deciding how substituted are they. One thing I want to say before we leave this topic, avoid calling these types of carbons primary, secondary, or tertiary. But you can call them more substituted or less substituted. And the reason is, when you start counting multiple bonds, it's hard to say Is it bonded to 2 carbons, or is it bonded 3 times to carbon? So we just don't say it. But we do often say more substituted, less substituted. On my alkyne, which carbon is more substituted? Yeah, the carbon on the left of the alkyne. This is more substituted because it has a bond to carbon. This is less substituted because it has a bond to hydrogen. Less bonds to carbon. Of my alkene carbons, right and left, which carbon is more substituted? You? The one on top. The one on the left of the alkene, because it's bonded to another carbon. The one on the left is not. More substituted, less substituted. And of my benzene, which of them is more substituted or less substituted? Equal. All equally substituted. Does that sound good? Reserve primary through quaternary for alkane type carbons, sp3 hybridized carbons. But we can use more and less substituted here. Okay? Why don't you guys take a quick break? Get up, get your blood flowing. Let's come back in 5.
No, I was just trying to
D, is that phone cover considered cheating in your biology classes?
Nah.
You sure?
Gonna check?
Doesn't have anything meaningful on it? The ribs, mandibular, mandibular, cervical spine. Oh, is that where your cervical spine is? Why would I have thought that was closer to the waist? Isn't the cervix in the hips? Never mind. Forget I said it.
Technically.
Is it? Right, right. But then why is the cervical spine up here? Am I crazy? Maybe, yeah. I think you're cheating if you bring this in. Look, the humerus, that's got to be an anatomy.
Help you.
It's got to be an anatomy term.
So it doesn't help me, so it's not cheating.
Fair. Okay.
Right?
Yeah. If you say it doesn't help, then I have to believe that totally.
Yeah.
Do you guys find this bag offensive? My old roommate got it as a Christmas present. She teaches middle schoolers. She said, if I bring this into class, they will kill me. She said, you want it? I was like, yeah, I think my college students will get a kick out of it. It's funny how when you mature a little bit, you can take things more lightly. You guys wondering what's in here? No, sorry. No, it's not candy. I've never been good at giving out treats or food. I've got my protein shake. It's molecules. with them for this next unit, this next part. So I'm going to take out the two that I don't want you to grab. And then I might have to start with just tables grabbing one, but I might come around and have you guys do pairs. So grab one for your table. This might be a good exercise for you to move together. There you go. Grab one for the table. If there's extra, I'll let you guys have more. One for the table. I feel like Santa Claus. The big heart. Oh yeah. Okay. And I'm gonna try to get Daisy over for you guys. All right. Maybe we're gonna do the exercise with these models. So I'm gonna give you over there so you can collaborate with theirs. All right. So in front of you, you've got this carbon chain. What would you give the root of your carbon chain? Oh. What would you call it? Butane? 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 Yeah, I wasn't very creative when I made them. You've all got a butane chain. Now, I want each of you to take turns doing this. Pick it up and notice how you can move it around. Why don't you choose the shape that you think this molecule of substituted butane would be most of the time? Does it take this shape? Does it take this shape? Does it take this shape? This shape? Do you have any guesses? Play around with it. Somebody's got to hold it. If nobody's holding it, you're doing it wrong. And then you should pass it around so everybody holds it. I didn't build these for you to just look at. You're going to have to touch them today. I have hand sanitizer if you want some. Have you decided on what shape you think it takes the most? What do you think? Okay. No, probably not. But what was your reasoning? Okay, so you've got them as far away from each other as possible? Not a bad idea. Put those big green ones as far away as possible. Some of you only have one group. Anybody else have another idea? Is that your answer? Did you move it? Did you restructure it? Don't. You didn't like take a bond off and break it? Uh-oh. Well then I made a mistake. Sorry. That yellow dot, is it coming off of the first carbon? Oh, sorry. I'll have to fix that. Anyways, don't change them because I made them specifically, but apparently I made them wrong. All right. So theirs is kind of just this straight chain, right? As opposed to the other group who had one of theirs kind of bent a little bit into a less easy to describe shape. Yeah? Do you notice how your molecules take up three-dimensional space? That's because that is their real shape. But we work on pen and paper or Apple Pencil and iPad. So we're limited to drawing three-dimensional things on a two-dimensional plane. So we need to communicate things about this three-dimensional shape in a two-dimensional plane. And then we want to communicate how it changes shape in three-dimensional space and what impact that has on its energy. Now, Natalie brought up a great point. They noticed that they had these two big green spots and they thought maybe they repelled. Repulsion is an important factor in considering the energy that a molecule has while it takes up space. But the way that it takes up space we call this conformations. Like, oh, don't let them conform you to their views. They're shaping you, right? That's the same word here. I'm shaping you to believe that 3D molecules exist and that they have different energies based on how they take up space. Cave to my conformation. We are going to look at one primary way of viewing these structures so that we can understand their energy more easily. But first, I want to start by representing these structures. So if you take your molecule and you straighten it into this zigzag line, you guys will notice that I have these groups on all of the carbons. Don't worry about that. Most of yours are shortened. Now, in front of you, draw it out, and let's turn it into bond line structure. One thing that I want you to point out once you've got this in a zigzag is that your center two carbons should have a group coming towards you and a group going away. A group coming towards you and a group going away. For you, at least one of those groups is a non-hydrogen. You've got a blue or a yellow or a green. We're going to draw those in. So on this carbon here, I've got a group coming towards me, a group going away, a group coming towards me, a group going away. Draw them in. If you've got blue, call it bromine. If you've got green, call it chlorine. If you've got yellow, call it SH. Or call it whatever you want to. I'm going to change your guys's so that I can get it. And just want to make sure that this is.
Yeah.
Good work. Why don't you add in the hydrogens that you see too? That's okay. Add your wedges and dashes so that you can see which ones are coming towards and away. And why don't we, instead of just using color, let's call it SH, the yellow group. But notice how yours is not coming towards you. This SH is going away from you, so it should be dashed. It's going to look different for you two because the SH is actually coming towards you. So here, you've got SH coming towards you instead of H. You agree?
Yes.
And if you move on to the last group, the dash, SH. Good. Great. Exactly what I see too. Oh, actually, I do see it a little bit differently.
Well, we didn't move it after we drew it.
Oh, okay. Because you would.
We had it like.
Okay, good. Because I was going to say,
Yeah.
yours goes down first.
Yeah.
With the
Great. That's good. I do want to point out, notice how yours, actually, you have a miso compound, so it's okay. I'll explain it. I'll explain it next week. This looks good. No, I was going to.
Are we supposed to draw it? Are we supposed to draw it?
Oh, wait, that was the thing.
Actually, I only want to like
Oh, yeah, that's so true.
you can just draw this.
Like magic sand or whatever.
And then you don't have to worry about those parts much. I just want to put the promise.
Yeah.
Okay.
Yeah, that's definitely.
Right. How do you guys do? You got it. Did you change it after you drew it? Oh, yeah. So would you agree that it looks more like this when you drew it? Notice how you got up and then a Burmese towards you, and then down and a Burmese towards you. Look at the bond goes up from CH3 to CHBr. Before, it went down in space and not down on your paper. Look at it. Do you agree that this zigzag does not agree with this zigzag? They're on a zig swath. But if it's this way, now they're in zig with each other. Yes, that's what I was looking for. I wanted to make sure that you drew it from your perspective, because it changes the molecule. And you did it right too, from this perspective. Same for you. And you had it like this. Great. Your structures look different based on your perspective, but they're the same structure. That's what I'm checking for. Okay, so you have all taken your zigzag. Have you noticed that all of our bond line structures are always zigzag? You've taken your zigzag molecule and you've sketched it out into a zigzag, highlighting the stereochemistry at those center two carbons. That's what we refer to this as. Regiochemistry is where in the molecule you're looking, but this zigzag is called stereochemistry. Conformations is an understanding of stereochemistry. What does stereo evoke in you? I think video killed the radio star? Not stereo, sorry. Stereo would be great for the radio star, right? Stereo surround sound, 3D audio experience. That's what stereo should invoke for you. Spatial. Stereo actually comes from the same word as, no, I lost it, sorry. But basically, stereochemistry is spatial interpretations. And we'll be talking a lot about stereochemistry. The reason that we draw bond line structures as zigzags, the reason that we imagine our 3D molecules to look like this and not to look like this or like this, is because we really are drawing these molecules in their lowest energy conformation. We're going to prove why this is the lowest energy conformation today and tomorrow, our next class. But we need to be able to draw them and represent them in their structures as well. And just because a molecule has a lowest energy conformation doesn't mean that that is where the molecule is reactive, or that's where we want the molecule to be. It also doesn't mean that's where the molecule is all the time. Catch? Did you move it at all?
Yeah, a little bit.
Give it back. Okay, me too. I twisted it a little bit. Notice how when molecules are moving through the air and running into things, they bump around and they move. The only thing that doesn't change is their bonds until something bumps into it hard enough to actually break that bond. But all of these conformations are allowed. That does get a little bit different when you look at rings. This does not have the same amount of freedom. It literally has lost a degree of freedom by being in a ring. It's able to still move around and bounce into weird shapes, but it's not able to go completely around. It gets limited at a certain point before it just bounces back in the other direction. Whereas your linear chains, these just spin around as much as they want to, endlessly. So what I want you to do is take your zigzag and put it 180 around that center bond. So now you've got a, not zigzag, but zig-zig. Sketch it out. It might be useful to try sketching it from the same perspective, a similar perspective you had at the start, but it's all right if you don't. And what did you guys call it? Call it SH? You know what functional group that is? As you're drawing it, what do you notice about the groups coming off of those two central carbons? How were they related before? How are they related now relative to each other? Or if you don't have two different groups, if you have just one, how did it change during this rotation? If I were to analyze my structure, it started here in the zigzag. I could call this hydrogen coming towards me HA. And as I rotate it, what happens to HA? It stays exactly the same. And that should make sense because I've got my methyl group in plane and then a wedge and a dash. And a methyl group in plane, notice coming down, coming down. This carbon on the left has not changed from conformation 1 to conformation 2. It has not changed its location in space. Now I'm going to label this hydrogen B coming towards me. That's this one. And as I rotate this group, where does hydrogen B go? It's now in the back. So during a rotation, we really only have to show the groups around one carbon moving. What's coming forward is going to end up going backwards. As I go into my zig-zig conformation, you guys understand why I'm calling it that, right? You understand zigzag versus zig-zig? I'm saying that you don't have alternating, just the same rotation every time. B rotates front to back. So you can try doing this with one of your hetero atoms. How did it move? Did it go from front to back, or did it stay front? Did it stay back? Then you can identify which carbon you actually rotated around. Now these are just two conformations. And what I want you to do is to draw a conformation that lies in between these two, where this methyl group, this CH3, is not in plane, but is actually wedged or dashed. And I apologize. We need two conformations where this methyl group is not in plane. First it'll be wedged or dashed, then it'll be the other, and then it will make it all the way around. So take your structure, feel free to go back to that original zigzag, but this time don't rotate it 180. Rotate it only enough that one of these wedge and dashed groups takes the in-plane position that the methyl had again. This is the structure that originally Natalie and Elliot put up. You want one of these other bonds, not the bond to the CH3, to be in plane with the rest of the structure. The CH3 will be wedged or dashed. Then do it one more time, one more rotation. Oh, I guess I was wrong. Sorry. I want to just correct what I have on the board so you have as clear directions as possible. You're going to go from this intermediate to here, and then there's one more structure. I'm going to redraw this over here in a minute to get back to this one. I'll come around in a minute and show you guys if you're setting it up correctly. So that's the one you've already drawn. That's the one you already drew. You've drawn two. So rotate it a little bit. Stop. Yep. And what you're going to do is keep this as in plane. Hydrogen, carbon, carbon, carbon. Your zigzags won't just be carbons anymore. Your zigzags include the hydrogen on one side. It's coming towards you, and it's going away from this. This is your plane. Wedged for you, dashed for you. So it is that, and let's put this in plane with these. So notice your zigzag. I guess actually is
This one is this.
your zigzag. Actually, this is more of a zigzag. It's going to include that hydrogen. So this is all in plane.
Oh, okay.
This is going away from you.
For the zigzag.
Yeah.
That's right.
That's it.
Okay.
Because your carbon chain is all zigzag.
Okay.
Yep. Yeah, and then make this your zigzag. Right. This is coming towards you. It's a wedge. Oh, so you just draw this. That's right. Yep, just draw a CH3. So you guys have this as your zigzag here. Yeah, CH3. It's okay, don't move it. You got it.
Oh, I get it.
Oh,
Okay.
okay.
You're right.
This is your zigzag. The hydrogen, I guess, one of the in-plane bonds of the zigzag. You guys got it? Here's your zigzag. The hydrogen makes up one of those zigzag bonds. You you guys are in more of a zig conformation, and that's okay. Here's your zig. CH3, carbon, carbon, hydrogen. So this should be a in plane, just like one of
That
those.
was the zig-zag.
Well, you can look at it too.
I know, but like.
But it's not a zigzag. This conformation is a zig. Because these two groups both point up.
No.
Okay?
You're right, that was what we just had. That was yeah, examine the pattern. Examine the pattern. Because it makes them like weirdly cut.
I did it.
That was our center.
So you should have your original zigzag, your original zig, a second zigzag where a hydrogen is in plane, and a second zig where a hydrogen is in plane. Those are the two other ones that you should be drawing, is where your methyl group takes a forward position and your methyl group takes a backwards position. At some point it should look something like this. So you've got your in-plane zigzags, and then you have wedges and dashes that are bisecting it. Do you agree with that? They go on one side of the point and the inside of it. Here, I want you to recognize that every vertex, they always come out on opposite sides. That seems like a small detail, but this breaks physics. And it's gonna, it's gonna make it impossible for us to actually interpret things about the molecule later. So this is perfect, and then the same thing, but with this H.
Does it matter if I put on this side?
Yeah. So to clarify, when you have a vertex in plane, it doesn't matter what your vertex looks like. The wedge and dash always come out of this vertex. You should never have a wedge on one side and a dash on the other. That breaks physics. You should always have your wedge and your dash coming out. I think I mentioned this before. It doesn't matter whether your wedge is on one side and your dash is on the other. If you actually drew it correctly, the wedge would always fully eclipse the dash. You'd never actually see it. So we just offset it slightly. Notice how over here I had HA wedged on the left and HA wedged on the right. They are exactly the same. They haven't changed. I have the choice. Neither of them is wrong. Both are correct. Both are wrong. Because they should actually be hiding the dashed group. But what I won't be able to accept is if you have a wedge coming off of one side and a dash coming through. If that bisects it, that's actually wrong. Okay? That's one thing I want you to be practicing with these two. Okay, so you guys have your, that's your zigzag, and you already did your zig, right? No? Okay. Great. What do you guys know? You've done them all? Great. I would have encouraged you to go, I should have caught it earlier. I would have encouraged you to ignore the stereochemistry on the CH3 groups, just because it clutters it more. Yeah. I wanted you to focus just on these simple carbons. I think that's a tough one. Try and redraw this one, and then just abbreviate CH3. This one though, so on this carbon you've got a dash, a wedge, and a plane coming off. But here you have 3 in planes and only 1 dash. I think your methyl group is supposed to be coming towards you, and this is like zigzag here, and you just missed it. But it might be good to also just redraw them all, abbreviate the CH3s so you can pull more attention to those other 2 carbons. So you can have it modeled kind of like that. Yeah? What do you guys think? So what I see are 2 zigzags. Instead, I think you should have 1 zigzag and 1 zigzag. So here's your original zigzag. Here, and I think you guys have this carbon cross. Here is if we rotate it to the back, which is what you have here. That's a zigzag. So your hydrogen comes up, the alpha group goes down, opposite of each other. And this is in the back. Then if you rotate it,
I like the class and like go home and do this because I don't like the class. So what you're saying,
For what I know, yeah.
I don't know.
Here,
I think I started with both of them. I started the zigzag formation with both of the blue ones facing.
Okay, so like that.
Yes, like this.
So now,
And then I rotated it down so that the blue left blue one is facing away.
so
feel free to copy that
if you go
model
like
down
that,
otherwise
see
from up
these are all
there
straight, you can
and
see.
just see
Yeah.
how
This
you can
one's going-
structure yours
You
to
just have to
fill
draw
in
this
with yours.
towards, at least according to me.
What do you think, guys?
Cool. I'm glad.
Here were your original 2.
Okay.
And then you got a
This is going straight
second
up.
zigzag and
Draw
then
the
another
jar.
zigzag. Instead, you should find 1 zigzag, 1 zigzag.
Oh,
So that can be challenging. So here was your original zigzag.
Oh,
If we rotate
I
this
totally get this. I was
like
Yeah.
this,
okay. So
this is a zigzag.
Yeah,
I'm
you're
sorry,
just changing what's
zigzag.
coming towards you and what's on.
Where methyl is going away,
like that, and then
chlorine is up,
And then
and
you'll
this
do it
other
other,
direction.
yeah, so. these
Then
are
we
fine.
rotate it one more time.
Up.
We did that original zigzag we did. Then we rotate it
Oh,
one more time.
okay.
And then methyl is
Yeah.
And then it moves back to the beginning.
So you're just kind of showing the different ways you could see it, like, four different ways you could see it. What
So I think
So you could see it.
this is a zigzag.
That is, thank you for
And this one might be
I was like, that's the only way.
zig. And methyl is back.
I just did not understand what I was actually supposed to be drawing.
What do you guys think? I think so. Good. Yeah. No, it's good. So you started here, you rotated the right-hand carbon, and the bromine got pushed to the back, the methyl got pulled forward. Then you rotate it again, and the methyl gets straight up, the bromine is back. Then you rotate it again. Yeah, it's good. Great job. All right. Part of this exercise's purpose is to help you realize that there's a lot of literally moving parts in these molecules. And from time to time in this section, we are going to want to take, not in just this section, excuse me, in this unit, we're going to want to take a molecule from one conformation to another. So one thing that I like to point out about these molecules is that this group of three coming off of a bond relative to a central atom, this group of three kind of behaves like a steering wheel, where you can rotate one part into the next. If I take methyl, I can rotate it into the wedged hydrogen, which puts the wedged hydrogen back and the back hydrogen in plane. Wedged methyl, back hydrogen, hydrogen in plane. Then I can rotate just a little bit more, and I can actually get it to be like my zig-zag, my zig-zig, which again can rotate. If I take my in-plane methyl and I push it back, then I'm pushing, I kind of forgot a hydrogen here. I can push this wedge, this dashed hydrogen wedged, this wedged hydrogen in plane, dashed methyl, wedged hydrogen, in plane hydrogen. That's what I wanted you to be looking for. Well, not what I wanted you to be looking for, but what I want you to kind of feel out now that you've seen it, is that you can take those three groups and you can kind of have them rotate positions. I pushed back the homework for section 3 because we're just starting to dip our toes into it right now. But I think I pushed it back to tomorrow night. I thought we'd finish it today. But I've never done this exercise before, where I've built these models and had you guys try to draw them. So you guys were a bit of a guinea pig. I think you could feel that. But ultimately, I am happy that you got a chance today to play with these and to move around with them. I'm going to be bringing them back tomorrow and next week so that we can talk about more properties that these compounds have. I'm going to push back your homework again. And I will say, you should be looking at section 3 and section 4 homework already. There's parts of section 4 that you can already answer, especially in regards to nomenclature. So don't wait. Start digging into both of them. They bleed in a lot, and I find that they're just really helpful to go hand in hand. So Wednesday, we're going to talk more about these conformations and ways that we view them with perspective. And then also we're going to talk about chairs and their conformations. Next week, we're digging more into stereochemistry and handedness. Okay, have a great night, guys. Happy studying.